Hello students. So today we are going to see some second part of the MCQs on solid state physics. So let's begin. So first question. So it is actually second part. So 25 questions are already discussed. So 26th question we will see the electrical conductivity of metals dot dot with increase in temperature. So we have to fill the blanks. So increases slightly, decreases, remains same, or none of these. So in order to solve this question, we have to know what is the electrical conductivity. So we have a formula for electrical conductivity, which is sigma, which is equal to N E square L divided by 3 K beta T into m raised to 1/2. Okay, so this is the formula for electrical conductivity of metals. So the sigma is the electrical conductivity, then N is the number of electrons per unit volume, E is the charge of the electron, L is the you can say length traveled by the electron, 3K beta, this is the Boltzmann constant, T is the temperature in Kelvin, and M is the mass of the, you can say, substance, or here electrons which are traveling in conductor. So we can say the sigma is inversely proportional to the square root of temperature. So as the sigma will increase if this temperature is decreased, or we can say sigma will decrease. Okay, sigma will decrease when temperature will increase. So now see the question: the electrical conductivity of metals dot dot with increase in temperature. So we have to see this condition: when the temperature increases, electrical conductivity decreases. So option number 2 is correct option. Now see the next question. So there may be number of questions that can be created based on this you can say formulas. So they may ask you what is the relation between sigma and, let's say, length traveled by the electron, or let's say sigma and n, so you can figure it out easily. Or sometimes they may give, instead of sigma, that is electrical conductivity, they will ask the rho, which is, you can say, electrical resistivity. So based on that, it will be just inverse of it, and based on that, questions will be there. The conductivity of a semiconductor dot dot with increase in temperature. Here also we have to write the conductivity of semiconductor or semiconducting material. Okay, so we should know its energy diagram. So this is our valence band and this is conduction band. Okay, so there is energy gap. So this energy gap is typically 1 electron volt. So in semiconducting material, as soon as we provide temperature to this semiconducting materials, the electrons travels from valence band to the conduction band, and as more and more electrons are available for the conduction, the conductivity increases. So the conductivity of semiconductor increases with increase in temperature. Okay, so we have seen from you can say electrical conductors, as soon as the temperature increases, the conductivity decreases. For semiconducting material, it is you can say as soon as the temperature increases, the conductivity also increases. So here option C is correct option. Now let's see the next question. For temperature greater than 0 Kelvin, the Fermi level can be defined as the level where the probability of occupation of the energy state by electron is. So we know for that purpose we have to see two things. One is this diagram. So let's say on y-axis we have probability of occupation, and on x-axis we have energy. So we have this diagram where probability is equal to 1, you can say, when temperature T is equal to 0 Kelvin. So at T is equal to 0 Kelvin, so x-axis is energy. So this energy is Fermi energy. Okay, I will write it as EF. Okay, so we have, just wait. So we have maximum field energy level at 0 Kelvin, that is Fermi energy. So this energy is Fermi energy. and this structure is at 0 Kelvin. If we talk about, we can say, higher temperature, at higher temperature, so this will pass through 1/2, and whatever this density, you can say, same energy, same energy levels will be occupied over here, okay, in this region. So these two areas are same, and it will not touch x-axis, though I have drawn it like that. So this point is 1/2, okay. So this is one point. So as the temperature, let's say this black color temperature is T1, so T1 is greater than T, so T here it is equal to 0 Kelvin. Now let's see it by the, you can say, Fermi distribution function, so which is f of E, which is equal to 1 upon 1 plus exponential raised to E minus EF, okay, upon k beta T. So we have to see the question again. For the temperature greater than 0 Kelvin, okay, so temperature is greater than 0 Kelvin, that is given. The Fermi energy, Fermi level can be defined as a level where probability of occupation of the energy state by electron is. So if this T is greater than 0 Kelvin, then obviously there are some energy levels which are greater than Fermi energy level. So we can say E is greater than EF. So this, you can say, numerator will be positive over here divided by this k beta T. So when this numerator, we have to check it for when energy is equal to, we have to check it when energy is equal to EF. This energy is equal to EF. So E, so we have to check the probability. So energy E is equal to EF. So EF minus EF, that will be 0. 0 divided by k beta T. So that will be 0. Okay. So exponential raised to 0, that is 1. So probability will be 1 upon 1 plus 1, so which is equal to 1 by 2. So we get a probability which is 1/2. So the half is the correct answer. So option 1 is the correct option. Now let's see the questions. So the velocity acquired by the current carrying particles per unit electric field is called as. So you know directly mobility, it is defined. So just wait. So mobility, that is the velocity acquired by the electron. So mobility, it is defined as velocity acquired by the electron per unit applied electric field. Okay, so let's say we have some conductor. So in this conductor, electrons are there. So electrons moves here and there without application of external electric field. So when we apply external electric field, electrons get you can say resultant you can say motion in particular direction. So down the, you can say, according to the potential difference. So the velocity acquired by these electrons per unit applied electric field, okay, so this is called as mobility. So directly we will get it, the second option is correct option, because this is formed by the definition of mobility. Let's see the next question. The Hall coefficient is, okay, directly proportional to the square root of the density of the charge carrier, inversely proportional to the density of the charge carrier, directly proportional to the density of charge carriers, and none of these. So in order to solve this problem, we should know simple formulas. So if you know the formulations corresponding to the Hall effect, we can solve this problem. So you know, okay, the Hall coefficient RH, it is given by -1 upon NE, where this, you can say, this N is the number of electron or electron density. So here we can see this Hall coefficient is inversely proportional to N. So it is inversely proportional to the density of charge carrier. So option number B is correct. So we have this directly proportional, this is inversely proportional. So it is inversely proportional to the density of charge carrier. Here in, let's say, conducting material, charge carriers are electrons. In semiconducting material, charge carriers are electrons and holes. So we have to directly get this answer by using this formula. Then let's see the next question. The ratio of the Hall field and the applied electric field is known as. So you can say there are some formulas. You can say you can expect more questions on the formula based on different, you can say, equations in the solid state physics. So here the ratio of the Hall field and the applied electric field is not known as. So we know that there we get angle phi, let's say. So that phi angle, which is defined as the Hall field, Hall electric field divided by externally applied electric field, let's say Ex. So this ratio is you can say, so this phi is called as Hall angle. So this ratio is defined as Hall angle. Okay. So in examination you can expect more questions related to the definitions or the related to the formulas. So let's see the next question. Which materials have the atoms without permanent magnetic dipole moment? Okay, so this question is very important. What is asked? Which materials atoms have atoms without permanent magnetic dipole moment? So you know, even in the paramagnetic material there are magnetic moments. Okay, so let's say these are the atoms, so magnetic moments are randomly oriented, okay, like this or like that. Okay, so they are randomly oriented and resultant magnetic moment is, let's say, 0. So resultant magnetic moment is 0, okay, but atoms has magnetic moment. Individual atom has a magnetic moment. So we have to see without. Okay, so without means paramagnetic has magnetic moments. Okay, so even we can say diamagnetic material has okay, so in these three materials if we compare, so diamagnetic materials get magnetized only if we apply external magnetic field, but there is no permanent magnetic dipole moment. That's why diamagnetic material is the answer. Ferromagnetic materials has magnetic moment and there are magnetic domains, that also you might have studied in the solid state physics. So diamagnetic is the correct answer. So what is the let's see the next question. What is the magnitude of magnetization vector? Okay, so magnetization vector, it is actually defined. Magnetization vector, it is defined as, let's say, m bar, which is summation of all magnetic moment vectors per unit volume. Okay, so summation of, let's say, I is equal to 1 to n, so summation over I. So mu I is the magnetic moment vector of individual atom. So it is sum of all magnetic moment vectors per unit volume. So we have to see the definition. So net magnetic moment per unit volume, or net magnetic induction per unit volume, net magnetic field strength per unit volume. So here we will understand that first option is correct. Okay, and permeability free space, this is just to, we can say, confuse you. So net magnetic moment per unit volume, this is the correct option. What is the magnetic susceptibility of the diamagnetic materials? So it is 1, positive, negative and infinite. You know, diamagnetic materials has magnetic susceptibility which is negative, that is for sure. So we have to see it is negative, and if it is negative, all other options has no meaning, because it is not 1, it is not positive, it is not infinite, of course. So third option C is correct. Let's see the next questions. The magnetic permeability for paramagnetic substance is ... permeability of free space, greater than, less than, equal to, or none of these. So magnetic permeability, if we talk about for the paramagnetic substance, is ... with the permeability of free space. So if you compare the magnetic permeability of free space and the paramagnetic substance, you can say the magnetic permeability of paramagnetic substance is slightly, you can say, very small, and it is slightly higher than the permeability of free space. So permeability gives us you can say material's ability to allow the magnetic lines of force to pass through it. So if you look from that angle, we will understand the permeability of paramagnetic substance is greater than the permeability of free space. Let's see the next question. Which substance or substances increase the flux density? So this question is quite tricky. So you know, let's say this is my material. So if it is kept in external magnetic field, let's say, okay, So this is external magnetic field. So what happens? Okay, so whenever this external magnetic field is applied, if this material is, let's say, diamagnetic material, so in that case it will get repelled. These magnetic lines of force will get repelled. If it is, let's say, ferromagnetic or ferrimagnetic material, that magnetic lines of force will pass through that material and magnetic flux density will increase. So we have to choose ferromagnetic and ferrimagnetic substances, because if, let's say, this is ferromagnetic or ferrimagnetic substance, so if this is magnetic lines of force, it will, you can say, get attracted and it will get passed through the material, and there is, you can say, more density of the you can say magnetic lines of force which are passing through this you can say material. So higher a number of that magnetic lines of force will, you can say, change their direction and try to go through the you can say ferromagnetic or ferrimagnetic materials, so their flux density will increase. So ferromagnetic and ferrimagnetic is the answer. Here there are some options. Only ferromagnetic, that is not true, because even ferrimagnetic materials we can say are the substances which increases the flux density. Now let's see the next question. In which materials the magnetic susceptibility is independent of temperature? So this question is also very important. Okay, so in case of paramagnetic and you can say ferromagnetic, it depends on the temperature. So for that purpose, if you have studied Langevin theory of paramagnetism, you will easily able to answer these questions. So for that purpose, you have to just see, I will just write the final formula for the Langevin theory of paramagnetism for let's say paramagnetism. So that value chi, it is given as n into mu square into mu 0 divided by k beta t. So here this is the susceptibility of paramagnetic substances, and the, you can say, you can easily see this n is the number of, you can say, just wait, number of atoms per unit volume. Mu is the magnetic moment of each atom, and the mu 0 is the permeability of free space, k beta is the you can say Boltzmann constant, and T is the temperature. So paramagnetic substance has the magnetic susceptibility which depends on temperature, whereas the susceptibility of, let's say, diamagnetic substance, it is independent of temperature. It is given by mu 0 n z into E square upon 6m, okay, into average of R square. So here we can see this diamagnetic susceptibility. There is no temperature term on the right hand side, so you can directly tick the question number answer number C, which says that diamagnetic susceptibility is independent of temperature. So even ferromagnetic, I think you must have studied the graph where, let's say, this is temperature and this is magnetization. So magnetization decreases with respect to temperature, and a point where the magnetization becomes 0, so this point is called as, you can say, Curie temperature, so above which that becomes paramagnetic substance. So this is also you can say ferromagnetic material also depends on the you can say magnetic susceptibility of ferromagnetic substance depends on the temperatures. This graph shows that. Now at which temperature the superconductivity is observed? Okay, so we know the superconductivity is observed at very low temperature, that is for sure. So temperature should be low. Low means that temperature should be below, let's say, 4-5 Kelvin. So for, let's say, lead or let's say for mercury, it is less than 5 Kelvin. So for, let's say, there are some materials and scientists are trying to get some materials with high you can say high TC materials. And one more thing that is required, that is magnetic field which is applied to that material, that should be less than critical field. So temperature should be low, that is for sure, but that temperature should be less than critical temperature, and the magnetic field should be less than critical magnetic field. So here there is a, you can say, very high, medium, low, and none of this. So nothing is said about the you can say external magnetic field which is applied. So we can say low is the answer for this, because at high temperature or medium temperature Medium temperature means you can say we will assume that it is room temperature, or let's say intermediate between its Curie temperature and transition temperature, critical temperature below which that material is superconducting material. Okay, so let's see the next question. Ideally, what is the electrical resistance of the superconductor? Ideally, electrical resistance should be 0. Okay, R should be 0, and in, you can say, in reality, this electrical resistance is very small. Okay, very small. So ideally, that electrical resistance should become 0 below critical temperature. Okay, which theory explains the superconductivity at the temperature close to absolute 0? So, there is only one theory which explains the superconductivity at temperature close to absolute 0. So, that theory is BCS theory. So, here it is given BCS and Langevin theory. So, Langevin theory is for the paramagnetism and diamagnetism. That is not for the, you can say, superconductivity. So only Langevin, that is also false. Only BCS should be the answer. So here, if you look at these 4 options, you will find that none of these, because only BCS theory is there, which explains the superconductivity at temperature close to the absolute 0. So why it is said close to absolute 0? Because at that temperature, mostly whatever superconductors are there, that will behave as a superconducting material. Let's see the next question. In BCS theory, individual electrons behaves. Okay, so individual electrons will behave as a fermions in BCS theory. Okay, individual electrons will behave as a fermions. Okay, even in BCS theory, but whenever there are Cooper pairs, okay, so we say that so individual electron behaves as a bosons. So let's say that I think that is the next question. The interaction between the electrons in a Cooper pair is the, okay, sorry, this is not the same question. So the interaction between the electrons in a Cooper pair is by the exchange of, you can say. So we will first complete this question. So here we fermion is the answer, so none of this will be the option. So the interaction between the electrons in a Cooper pair is by exchange of. So exchange of phonons is the answer, because in Cooper pairs, you can say electrons get combined and electron behaves as a bosons, and there is exchange interaction between these Cooper pairs, and these exchange interactions are through phonons. You can say phonons are nothing but lattice vibrations. So because of that, there is exchange interaction. So if you study this theory, BCS theory, you can say correctly, you will be able to answer these questions. A bulk superconductor in a weak magnetic field acts as a perfect. Okay, we have to write the correct option. So bulk superconductor in a weak magnetic field. So first thing, it is superconductor, it is in weak magnetic field, acts as a, you can say superconductors are perfect diamagnetic materials. Okay, so none of these will not be there. Diamagnet, okay, it acts as a perfect diamagnet, that may be the correct option. Ferromagnet will not behave as a ferromagnet, and or cannot be there, because superconductors are basically diamagnets. So they are perfect diamagnets below Curie temperature whenever they are behaving as a superconducting material. So one more thing, whenever material behaves as a superconducting material, their also, you can say, magnetic susceptibility value is -1. So that asked. Okay, so superconductors in the Meissner state exhibit perfect. Okay, in the Meissner state, they will, you can say, exhibit perfect diamagnetism. Okay, so Meissner state means below critical temperature and less than when the magnetic field, applied magnetic field is less than critical magnetic field. Okay, so next question. The superconductor with little or no magnetic field with it is said to be in this state. Just now I have told it is in the Meissner state. Okay, so that is, you can say, Meissner effect is related to this, so it will be called as Meissner state. According to BCS theory, electrons in a Cooper pair behave as, okay, here is that question. So electron will behave as a, you can say, bosons in, you can say, Cooper pairs. Okay, independent electrons are fermions, but in Cooper pairs, electrons behaves as a bosons. Okay, so that is the, you can say, answer number C. Okay. In a paramagnetic substance, each atom contains dot dot magnetic dipole moment. Okay, each atom contains permanent dipole moment, but that permanent dipole moment is very small in quantity. So overall magnetic moment is zero. That also we have seen, and it cannot be infinite. Okay, that's why we have ticked the second option. Paramagnetism is shown by the atoms which have dot dot electrons. So for paramagnetism to be shown by you can say some atoms, so there must be unpaired electrons. This is the basic condition for any type of magnetic materials. So if there are you can say one unpaired electron, that will show paramagnetism, or let's say 2-3 unpaired electron, that will show ferromagnetism. If let's say there are 5 or more unpaired electron, that will show ferromagnetism, and like this way. So we have different magnetism depending on the amount of magnetization that we obtain. So definitely we can say paramagnetism, or paramagnetism to occur, there should be unpaired electrons. So let's see the next question. The temperature above which the ferromagnetic substance becomes paramagnetic is called. So ferromagnetic becomes paramagnetic. So that is nothing but Curie temperature. So there is one more thing. Whenever antiferromagnetic material becomes paramagnetic, that is called as question. So at sufficiently high temperature, all transitions and rare earth metal becomes. So generally all transition and rare earth metals are magnetic materials, but at sufficiently high temperatures, that materials will get converted into paramagnetic material. So option A is the correct option. So with this I will stop. Thank you for watching.